What if you could instantly get like 10% more horsepower out of your body without actually trying any harder,
Right.
just by turning your wrists upside down?
Right. Yeah, it sounds totally like a parlor trick, doesn't it?
It really does. But today, we are doing a deep dive into how a tiny, almost imperceptible adjustment in your grip can completely rewrite the way your muscles and your brain communicate during intense physical exertion.
Yeah, and the underlying neurophysiology here is incredibly robust. I mean, we are looking at a 2024 study that was published in the Journal of Sports Science and Medicine.
That's awesome.
Yeah, it was led by Shahab Alizadeh and a really dedicated team of researchers, including Edwards, Lockyer, Holmes, Power, Behm, and Button. And they basically set out to bridge this critical gap between biomechanics, so, the physical levers of your body, and the central nervous system, which is what actually drives those levers.
Like the brain's wiring.
Exactly. And the goal today is to lay out these findings with real scientific clarity so you, the listener, can visualize the complex mechanics of human movement happening right under your skin.
Okay, let's unpack this. Because what makes this research so approachable is that it focuses on something you have probably seen or done 100 times, right? Arm cycling.
Oh, yeah, definitely.
It's a total staple in athletic training rooms and physical rehabilitation clinics. So, if you ride a standard bicycle, you know that adjusting your seat height by even half an inch completely changes your leverage.
Oh, for sure.
You suddenly feel tension in your quads or your hamstrings that just, well, it wasn't there before. But this study isn't about seat height or even your legs, right?
No, not at all. It is entirely about the rotation of your forearms while you are pedaling a bike with your hands. The researchers asked this deceptively simple question: does flipping your grip 180 degrees alter the mechanical power you produce?
And does it change the actual neurological signals the brain sends?
Exactly. So to figure this out, they brought in 14 healthy adult males to perform what's called an upper body Wingate test.
Right.
And they did this on a highly calibrated scientific-grade arm bike, a modified Velotron ergometer.
So for people who don't know, what exactly does an upper body Wingate test look like?
So it involves 30 seconds of absolute, all-out, maximal arm cycling against a heavy mechanical brake. And they set that brake to 5% of each participant's body weight.
Wait, only 30 seconds?
Right.
I mean, why put people through 30 seconds of torture just to see which way their hands are facing? Is there really that much to learn from half a minute of exercise? You would think a longer endurance test would yield a lot more data.
Well, what's fascinating here is that 30 seconds of absolute maximal effort actually provides the perfect physiological window to observe the rapid onset of neuromuscular fatigue.
Oh, I see.
Yeah, like during endurance tests, the body settles into this comfortable pacing strategy, but when you ask the body to just empty the tank completely in half a minute, you force the central nervous system to scramble.
It's in panic mode.
Basically, yeah. It has to rapidly adapt to overwhelming mechanical stress. And that scrambling, that desperate search for efficiency as the seconds tick by, it reveals the true underlying neurological hierarchy of how we move.
That makes a lot of sense. So let's talk about the core variable here. They tested these participants using two specific forearm positions.
Right.
The first was the pronated position, which is where your palms are facing down away from you, kind of similar to gripping the handlebars of a mountain bike.
Exactly.
And the second was the supinated position, where your palms are facing up and towards your body, like you were holding a barbell for a bicep curl.
Yeah, perfectly described. And the data collection here wasn't just asking the guys which grip they liked better. The scientific rigor involved is what makes this paper so compelling.
They went deep.
Oh, they really did. They used surface electromyography, or EMG, to track the real-time electrical activity across the upper body. Instead of just looking at the arms, they tracked 5 specific muscles.
So which ones were they watching?
They monitored the biceps brachii, the lateral head of the triceps brachii, the brachioradialis in the forearm, the anterior deltoid, so the front of the shoulders, and the latissimus dorsi in the back.
Wow, so they are actively watching the brain's electrical signals tell these specific muscle groups to fire.
Yeah, and at the exact same time, they measured the physical forces at the pedal-crank interface. They separated these into normal forces.
Which are the up and down movements, right?
Right, the perpendicular forces that don't actually rotate the pedal.
Yeah.
And then the propulsion forces, which are the forward and backward forces that actually drive the crank in a circle.
Okay, so we have this incredibly detailed map of both the electrical input from the brain and the physical output at the pedals. To understand the true impact of this test, we have to look at the scoreboard first. Who won the power battle, palms up or palms down?
The pronated position, so palms down, was the clear, undisputed winner for overall power.
Really?
Oh, yeah. It produced a 5% higher peak power, an 8.5% higher average power over the full 30 seconds, and an 11.6% higher minimum power output compared to the supinated position.
Wait, 11.6% higher minimum power? That seems massive.
It is a critical metric. I mean, minimum power represents the very end of the test, right? When the participant is absolutely exhausted. The fact that having their palms down allowed them to grind out significantly more wattage in a state of severe fatigue, well, it indicates a fundamental shift in mechanical advantage.
But reading through the sources, there is this perception paradox that really stands out to me. Despite generating significantly more power in that pronated position, the rate of perceived exertion, the RPE, was identical.
Yeah, it's wild. The researchers used the Borg scale, and in both tests, the participants rated their effort as 16 or 17, which translates to very hard.
Here's where it gets really interesting for anyone listening. Getting more power for the same perceived effort is like tuning your car's engine to get 10% more horsepower without burning any extra gas or feeling the engine strain.
That's a great way to put it. The brain registers the exact same level of systemic effort, but the physical output in the real world is tangibly higher. But to see if they could predict this performance, the researchers brought in another fascinating metric.
Right, hand grip strength.
Exactly. Before the cycling even began, they tested grip strength in both standing and seated positions.
And this is where my brain broke a little bit. Only the seated grip strength showed a positive correlation with peak power output during the Wingate tests.
Yep.
I mean, why would sitting down to squeeze a dynamometer predict your arm cycling power better than standing up? Aren't your hands doing the exact same thing?
It's a great question, and it requires a shift in how we think about muscle isolation. You see, the central nervous system doesn't operate muscles in a vacuum. It operates them in functional chains.
Oh, right.
So the seated grip test more closely mimics the exact postural and biomechanical demands of the seated arm cycling test. When you sit down, your core stabilization and your shoulder alignment completely change.
So proving that functional strength is highly context-dependent.
Precisely. It's totally context dependent. But, knowing that the pronated posture generates more power is cool, but to understand why, the researchers had to slow time down.
Right, and look at a single 360-degree pedal stroke.
Yes, and they used a unique technique for this called statistical parametric mapping, or SPM.
Because normally, sports science studies just grab the average power, right? Like taking snapshots of a race.
Exactly. But SPM gives us a continuous time series analysis. Instead of averages, they looked at the entire 360-degree pedal revolution to see exactly when and where muscles fired.
Okay, so break that 360-degree pedal stroke down for us.
Well, during the pushing phase, which is the first quarter of the stroke, the pronated position produced a much greater pushing force and upward normal force.
But then it changes during the pull, right?
It does. During the pulling phase, roughly around 164 to 219 degrees of the revolution, the supinated position actually generated greater propulsion force.
So it's literally like a biomechanical game of tug-of-war versus pushing a stalled car. Supinated gives you the mechanical advantage to pull, but pronated gives you the ultimate advantage to push.
That is exactly what the EMG findings showed regarding muscle synergies.
And a synergist is basically a muscle that collaborates with another one to execute a movement, right?
Yes. So during the pushing phase, the triceps brachii and anterior deltoid acted as synergists working together. But during the pulling phase, the biceps brachii, brachioradialis, and latissimus dorsi acted as synergists.
Okay, so different teams tag in. Where does the pronated advantage come from?
Well, the pronated position specifically allowed for a greater neuromuscular advantage for the anterior deltoid during pushing. If we connect this to the bigger picture, this shows that changing a joint angle by just 180 degrees shifts the entire workload distribution across the upper body.
Which is mind-blowing.
Yeah.
But everything we just discussed is how the body works when it's fresh. What happens when the clock ticks past 15 seconds and the muscles start screaming?
The evolution of fatigue in this test is fascinating. As you'd expect, propulsion force constantly decreased from the beginning to the end. But the way the muscles reacted was bizarre.
How so?
Muscle activity in the triceps and anterior deltoid actually decreased over the first 180 degrees, but then increased during the last 180 degrees as fatigue set in.
Wait, so they're producing less force in the push, but lighting up more on the EMG during the recovery phase of the circle?
Yeah. The central nervous system is desperately trying to compensate and keep the pedals moving, and one muscle in particular just completely burns out.
The triceps.
specifically the lateral head of the triceps. It is highly susceptible to early fatigue because it acts as a primary synergist almost exclusively for elbow extension. It just takes a massive beating.
Ouch. And while the arms are failing, there is this totally bizarre phenomenon with hand dominance, right?
Oh, this was a mind-blowing finding. So in the first quarter of the pedal stroke, the dominant hand produces the most propulsion force.
Makes sense.
But as the pedals transition through the bottom and top of the stroke, the non-dominant arm takes over and produces greater propulsion force.
Wait, is the dominant hand just acting like an overeager sprinter that gasses out early, leaving the non-dominant hand to carry the load and finish the marathon?
It really looks like it. And this raises an important question about neurological strategy. At any given section of the cycling revolution, the brain shifts the primary driver to one arm while the other assists.
So it's an intentional relay race.
Yeah, this alternating force strategy might be the central nervous system's way of managing localized fatigue, buying tiny milliseconds of rest.
That's incredibly smart.
It is. Furthermore, the supraspinal drive, which is the brain's actual signal sent down to the muscles, likely diminishes as the Wingate test progresses.
Right, a sign of central fatigue. It's like a circuit breaker tripping to protect the house from overloading.
Exactly. The brain reduces the electrical signal, causing that unavoidable drop in power.
Wow. So wrapping this up, what are the practical takeaways for you, the listener? If you are an athlete using arm cycling for performance, pronation gives you peak absolute power, period.
Yep, the data is very clear on that.
But if you are in rehabilitation, for instance, managing spinal lesions, you can deliberately choose supination or pronation to target specific neural pathways and muscle groups.
Exactly. You aren't just guessing. You are selecting the exact wiring you want to activate. And I really encourage everyone to read the full article by Alizadeh et al. In the Journal of Sports Science and Medicine.
Yeah, the visual data is amazing.
It really is. Viewing the incredible 360-degree SPM charts for themselves is highly recommended.
And if you found this conversation helpful, please follow the channel and turn on notifications for more deep dives into cutting-edge science.
Absolutely.
I want to leave you with a final thought to mull over. We just saw how simply rotating your wrist can completely rewrite which muscles your brain decides to recruit and exhaust during 30 seconds of exercise.
It's a huge shift from such a small movement.
It really is. It makes you wonder, what other tiny micro adjustments in your daily posture or grip are secretly changing the entire neurological map of how you move through the